This 3D printer is a fascinating fusion of mechanics and chemistry. Here's an example of some objects it's created. In this tiny, exquisite swan, the details in it are resolved to nearly 50 microns, or 2/1000ths of an inch. As I focus the eye, look at the detail, and then notice the ripples on the wings. Or look at the features in this small boat it printed. In this peacock feather, you can see the fine details it can create. The most familiar type of 3D printer melts bits of plastic filament to create an object. That's called FDM, or fused deposition modeling. This, though, is a stereolithography 3D printer. Stereolithography printers, often just called SLA printers, use light to create an object. In this video, I'll highlight some of the engineering choices and the science underlying SLA printing. On a fundamental level, all 3D printers, FDM, SLA, and other types as well, all work in the same way. They take a 3D model, slice it into many thin two-dimensional slices, and then they print these slices one at a time, one on top of the other, to create a three-dimensional object. Let's watch the printer in action. The swan will be created right here on the lower side of this print head. The print head descends into this amber tray, which contains the liquid resin. And there you can see it settle into the resin. And let's watch the action right here on the print head. Here's a close-up. The printer exposes the first layer, that's the flash of light. Then the tray slides sideways, and the return so another layer can be added. You can't see anything yet, but I'll speed everything up and then there. You see in about 30 minutes the swan appearing. And by about an hour, the swan is done. You see it here attached to the print head. Now, let's examine every step or motion that's used to print this swan. Let's start with that flash of light. It's blue light, although it looks yellow-green because it was filtered by the orange tray. In the tray is liquid resin, which solidifies when exposed to blue light. I filled this watch glass with a bit of the resin. Watch what happens when I shine the blue laser on it. Almost instantly, the resin solidifies. It's called curing. Of course, what I did with this laser pointer was pretty crude, but this printer uses a DLP, a Digital Light Projector, to shine light with great precision to create a layer. The tray has a clear window, so light flashes can cure a layer. This is the base of the printer. Sitting on the base is the amber tray that contains the resin. Note that the silicon-coated window of the tray is positioned over a window in the base, and inside there's a bundle of electronics that contains a powerful LED, a light-emitting diode. It produces blue light of a narrow range of wavelengths. Then a lens spreads that beam of light and shines it onto a mirror. That mirror then reflects the light through the window in the tray and onto the resin. To see these images, I'll put a yellow card right here where the layers are created. Remember that what we are looking at here are the layers of the swan, which are printed one by one on top of each other. As we watch the layers, keep in mind the printed swan. Here, the thin red line in the yellow block of the swan indicates the cross-section being printed. In the projected images, the bright blue areas are where light is reflected on the resin and cures it. The dark areas reflect no light on the resin, and so it stays liquid. Notice the round circles. These are the support posts created when the swan prints. They're more easily seen here when highlighted in blue. These are later snapped off the swan. Let's speed up the printing and watch the swan being formed. All the tiny circles coming up are the support posts at the very bottom. Here, the base prints. And then the body. You can see the wings begin to take shape. Now we have just the wings and the neck. The neck's the round blue dot on the right. And as we reach the top of the swan, you see only the tips of the wings, and then the flashes disappear. So, we've now seen the essential sequence that occurs 444 times to create the swan. A flash of light to cure the resin, the swing of the tray sideways, and then it's returned to print another layer. While the tray swings sideways, the print head moves up 100 microns. Notice that the ember prints the swan upside down. It's called bottom-up printing. This dramatically reduces the amount of resin needed to print the swan. In stereolithography printing, there are two main ways of doing this, the bottom-up used here and top-down printing. In top-down SLA, a platform moves down into a vat of resin while light is projected down from the top. This top-down method has a very big drawback. The vat must be as tall as the part to be printed, and this requires a large volume of resin, which can be very expensive, particularly if the resin has a finite lifetime. In contrast, the bottom-up method uses a shallow tray that requires a much smaller amount of resin, even for tall parts. I find it stunning to watch a large object being drawn out. Next, let's look at why the resin tray slides sideways after each layer. In a bottom-up print, the layer is built on a window. One of the key problems with bottom-up printing is being sure that the most recently printed layer doesn't stick to the window. This window is silicon coated, which is permeable to oxygen. That allows oxygen to flow to the layer, and this oxygen inhibits curing at the window layer interface. Yet, even with this silicon window, the newest layer will still partly adhere to the window. If it does, then no fresh uncured resin will be able to be added, and so no new layers. So the newest layer must be separated from the window. There are several ways to do this. Some printers just pull the layer up, yet this direct pull, as it's called, can create problems. The layer is like a suction cup. Even this tiny suction cup can lift this heavy piece of plate glass. And so to separate layer and window requires a large motor to lift the print head. This action might damage the layer. A suction cup, though, can be more easily removed by lifting an edge and sliding the suction cup. In general, the force from pulling up scales as the fourth power, the length of the piece in the XY plane, while sliding scales as the square. So typically sliding requires 1/100th the force of pulling up. And for this reason, this printer slides the tray to separate layer and print head. Other printers peel the layer off the window with a rocking motion. One way that a 3D print on this machine can fail is that the cured resin can get stuck to the window. Most 3D printing resins have the interesting property in that the presence of oxygen hinders the chemical reactions that cause the cross-linking of the oligomers. Because the window is made from silicone, a material highly permeable to gas, oxygen residing in the window diffuses into a thin layer in the resin just above the window. This layer is thin, on the order of 5 to 50 microns thick, but the concentration of oxygen in this layer is enough to prevent the resin curing directly on the window. The window on resin trays in bottom-up printing must be transparent to blue or UV light. And the three most common materials for windows are a thick layer of silicone, like in this machine, a thin film of Teflon, or a sheet of glass. Each has its advantages. Silicone windows have a very high oxygen permeability, which allows for a large oxygen inhibition layer. But the silicone is relatively soft. It can wear down over time, and some components from the resin can diffuse into the silicone and cloud the material. The clouding blocks light, and eventually the window must be replaced. Teflon films have very good chemical resistance, and oxygen permeability can be controlled by choosing the thickness of the film. Thin films can also be delicate and may suffer from a large amount of deflection. Glass windows provide great rigidity and chemical resistance, but are not permeable to oxygen. Without an oxygen inhibition layer, the printer can still work, though it may be slow or suffer from very large separation forces. We've been looking at the mechanics of how the printer works, but as I said at the beginning, this is a triumph of both mechanics and chemistry. The combination of precise motion with fine-tuned chemistry creates the resolution of this printer. There are 4 main ingredients in the resin. First, the resin contains a photoinitiator that, when struck by blue light, starts a chemical reaction that links together the next 2 components, short hydrocarbon molecules. These short molecules come in 2 sizes, a monomer and an oligomer. The latter is just 3 or 4 monomers bonded together. It is the balance of these two that yields a swan that is rigid and well printed. leave out the monomer, and the resin is very viscous and can be very slow to print. And equally disastrous is leaving out the oligomer. Here's a tiny boat that we printed. If I squeeze it, you see that without the oligomer, it's no longer rigid, and in fact, it even breaks. And equally dramatic is leaving out the fourth component. It's a UV blocker. It prevents the blue light from penetrating too much past the layer being printed. Here's the boat printed with UV blocker. You can see the resolved details in the boat. Keep your eye on the circular hole in the middle. Here is the same boat printed without UV blocker. Without it, the light cures regions of the boat that were meant to stay liquid and lowers the resolution significantly. Now, the most stunning part of this printer is how the mirror reflects the layers onto the resin. In the optical train, there's a small chip about 3/4 of an inch by 1/4 of an inch. It's a micromirror. It's comprised of a bit over 1 million tiny mirrors, each about 8 microns by 8 microns. Recall that a human hair is some 80 microns, so a single hair would cover about 10 of these mirrors. This drawing shows 2 of the mirrors. Each of the mirrors can be controlled separately. An electrostatic force generated by a small voltage pivots a mirror plus or minus 12 degrees. This directs reflected light either onto or away from the resin. Because these mirrors are so tiny, light can be directed to 10 micron sections of the layer, so the printer has a high resolution in the XY plane. Underneath the mirrors is a slender post. It's a mere 1 micron or so, and below that, an elaborate yet tiny hinge. It would seem that such an assembly would be fragile. You picture 1 million hinged mirrors clattering back and forth as this machine is moved. Yet that's not true. The mirrors are so small that they don't respond to the vibrations and shakes from normal handling. Nor does that pivot wear out easily. Tests show that the mirrors could continuously flop back and forth for 11 years before the pivot fails. Now, the light source in an SLA printer could also be a laser. In fact, several commercial models use them. In contrast to a digital light projector, the laser must raster across the layer, so it's slower than a light projector. Also, the precision of the printer is determined by the spot size of the laser and mirrors that rotate to direct the light, a mirror galvanometer as it's called. Compare this to a light projector where the resolution depends on the distance from the projector to the focal plane and thus is adjustable with optics. The laser, though, is cheaper than a light projector. There's, of course, much more to be said about an engineered object like this, so I've linked to other videos that might interest you. I'm Bill Hammack, the Engineer Guy.